we are going to continue our discussion of extremal graph theory. Last time we discussed what happens when we exclude a triangle, or more generally a clique, and we wish to find a graph that maximizes the number of edges. And at the end of the lecture, I stated the theorem of Erdős, Stone, and Szymonovitch, which says, recall, that if you have a fixed h, and I wish to understand the maximum number of edges in an n-vertex graph that is h-free. So remember this definition. This is the maximum number of edges in an n-vertex h-free graph. Okay, so we're going to be looking at this quantity in the next few lectures. So the Erdős-Stone-Szymonovitch theorem tells us that perhaps quite surprisingly, this quantity is largely governed by the chromatic number of h, even though h itself might be quite involved. So if you knew the chromatic number, you already know a lot of information about the growth rate of this function. And in particular, as long as h is not bipartite, so that the chromatic number is at least 3, we already know the first-order asymptotics from the Erdős-Stone-Szymonovitch theorem. However, when h is bipartite, so that the chromatic number is exactly 2, then the theorem tells us only that this quantity is little o of n squared, which is some useful information, but it doesn't tell us the whole story. And in the next several lectures, I want to explore what more can we say about this quantity here for bipartite graphs H. And it turns out that there's a lot that we do not know. There are lots of open problems in this area having to do with trying to pin down the growth rate of this function. And in particular, for bipartite graphs, there's a bipartite graph that plays a somewhat special role, namely the complete bipartite graph. So KST being the complete bipartite graph with S vertices on one side and T vertices on the other side. So this is a very nice bipartite graph. And just to understand the extremal number for this graph is a famous open problem in this area. And it has the name of Zirin-Kevich problem. Which is to determine or estimate the extremal numbers for these complete bipartite graphs. Okay, so I'll tell you pretty much all we know about this problem. There's some interesting things, but we do not know all that much. Now, every bipartite graph is a subset. It's a subgraph of such a complete bipartite graph. So every bipartite H is a subgraph of some KST. And we know that if H is a subgraph of this KST, then the extremal number for H, well, if your graph is H-free, then automatically it has to be KST-free. So there is this bound between these two extremal numbers. So in particular, if you have some upper bound on KSTs, then you have some upper bound on bipartite graphs. Although for specific bipartite graphs H, maybe we can do better than using this bound. And we'll see examples of that later in the course as well. Okay, so what can we say about the extremal numbers of these KSTs? And so the most important theorem in this area of this problem is the result due to Kővári, Zhao, and Turán. so the Kővári-Turán theorem, tells us that for every fixed integers s and t, s at most t, there exists some constant c such that the extremal number is upper bounded by something which is on the order of n to the 2 minus 1 over s. Okay, so it gives you some upper bound, showing you that it is not only subquadratic, but there's a gap from 2 in the exponent. Now, in combinatorics, as is with many fields of mathematics, it can be somewhat intimidating to newcomers when you see a lot of names. Or every theorem seems to be named after a string of mathematicians. Some of you may have heard of, some may not. And I agree, it's kind of maybe difficult to remember who is who and what is what. But I think this theorem has a very nice way to remember, which is that it's a theorem about KSTs, and this is the KST theorem. Okay, right, so this is the KST theorem. I want to begin by showing you how to prove the KST theorem. The proof is via a nice, not too difficult double counting argument, and then show you some applications. Right, so let's prove this theorem, and it's by a double counting argument. What are we going to count? Well, let's start with the object that we're working with. So there's going to be a graph G that has n vertices, m edges, and KST free. And let's count the number of stars, ks1, in this graph G. So we're counting configurations like that. Do an upper bound and a lower bound. On one hand, so let's start with the upper bound. On one hand, every subset of S vertices in the graph G has at most t minus 1 common neighbors. Because if they had t common neighbors, then you get a KST. Okay, so that's one bound. On the other hand, let's see what happens to the number of common neighbors if you knew that this graph has a lot of edges. So the number of stars, well, I can calculate this quantity explicitly by running over all the vertices of G. For each vertex, look at its neighborhood and choose S vertices from its neighborhood. So from each V, I need to find a subset of S vertices from its neighborhood. By convexity, I can lower bound the sum by the average in some sense, because, okay, let me first write down the expression. So I can do a convexity argument that gives me this lower bound. Here, I'm abusing notation somewhat and writing binomial coefficients with a real entry on top, where I mean the expression, as you would expect, treating this guy as a polynomial in X. And the key fact we're using here is that this function here is convex for X at least n minus 1. So in particular, if you think about this function here, we have a lot of zeros, and then it becomes convex afterwards. So you can even think of extending this function as 0 to the left of n minus 1. So this is a convex function, and you can apply convexity to deduce this inequality. But you know the sum of the degrees. That's just essentially twice. I mean, that is twice the number of edges. So we have this expression right here. So you have an upper bound on the number of S stars coming from KST freeness, and lower bound on the number of S stars coming from just having lots of edges and applying convexity. Okay. Putting these two things together, we find that there's this inequality here. Here, we are thinking of S and T as fixed, and we are trying to understand how M and N depend on each other as they get large. So it will be helpful to use the asymptotics that N choose S grows like N to the S divided by S factorial for fixed S. So looking at that expression and applying this asymptotics to both sides, we have this inequality here. So I've eliminated S factorial from both sides. Okay, so now rearrange, clean things up. We find the following upper bound on M, the number of edges in G. And that's the expression. So for fixed S and T, it grows like N to the 2 minus 1 over S. Any questions? Yeah.
Where does the right side of the inequality come from? How are you counting that from every side?
So the question is where the right side of inequality, which inequality? This one here? Right. So here we are counting the number of KS1s. So here I am upper and lower bounding the number of KS1s using what we derived earlier. Yes?
Do you actually care that S is less than or equal to T in the argument?
Right, the question is, do we care that S is less than or equal to T in the argument? The argument doesn't care, but of course, if you want the better asymptotics for fixed S and T as n gets large, you should take S to be less than or equal to T. Question? What happens when T equals to 1? Well, that's a great question. I'll leave you to think about it. If you know that your graph has maximum degree at most T, what can you tell me about the number of edges in the graph? Okay? Any more questions? Okay. We'll come back to this theorem. In fact, this will occupy us for at least a couple of lectures. Basically, is this theorem tight? And it is conjectured to be, although that is a major open problem in extremal graph theory. We only know a small number of values. Well, for most values of S and T, in particular, when S and T are both equal to 4, we do not know if this bound is tight. But there are some values of S and T for which we do know that it is tight. For example, 2 and 2, 3 and 3, 4 and 7. S and if T is really, really large. And I will show you some constructions later on creating graphs G that are KST free for those parameters that matches this KST bound up to a constant factor. Yes?
For fixed S, what's the bound on T? Is there like a bound on T first to get like equality cases?
Right. So the question is, for a fixed value of S, is there some bound on T for which we get equality cases? There's a conjecture that this bound is sharp up to a constant factor for every s and t. But we only know how to prove that conjecture, and I will tell you much more about it later on, when t is much larger compared to s. Yeah, so there are lots of unexplored territory on this problem. Any more questions? Okay. Before diving into the Kővári-Sors-Turán theorem further, I just want to show you some neat applications. And I want to begin with a geometric application. There's a classic problem asked by Erdős back in the 40s called the unit distance problem. Which asks, what is the maximum number of unit distances? The maximum number of unit distances formed by n points in the plane. Let me give you some examples. If you have 3 points, you put them in an equilateral triangle, and all 3 distances are units. Great. If you have 4 points, you cannot place them so that all 6 distances are units if you stay in the plane. So the best thing you can do is something like this. Okay, so I'm drawing all the edges that are unit distances. If you have 1 more point, turns out that's the best thing you can do with 5 points. With 6 points, there are some more possibilities. Let me draw for you some possibilities. You can extend the previous configuration by adding more triangles. And there are many different ways that you can attach an extra triangle. There's actually one more way to do it with 6 points. Namely, I can put them like a projection of a prism. Right, so all of these configurations have the maximum number of unit distances attained if you draw 6 points. Okay, if you draw 7 points, turns out this is the best way to do it. Okay, so you can go on for a while, and people have. Okay, so you can try to tabulate for every n what's the maximum number of unit distances you can generate having n points in the plane. And the question is, what is the answer for n points? And it turns out for this problem, and for many problems like it in combinatorics, you can have a lot of fun with playing with small examples, but they are often misleading. It doesn't really tell you what the overall structure should be like. And it turns out this is a major open problem for which we do not understand what the structure is like for large values of n. So think n large. What are some possible ways to generate many unit distances? Yep. Great. So one way is to draw lots of triangles. Right? So extend this figure forward. Okay, so let's do that. Well, actually, let me give you something even simpler to begin with. I can just put the n points on the line, equals spaced. Okay, I get n minus 1 distances, n minus 1 unit distances. Right, if I put them like that, right, how many unit distances do I get?
2 times n minus 1.
All right, 2 times n minus 1. Right? So each new point gives you 2 extra new distances. Okay. And you can try to think about how to do better. Well, if you follow that sequence of examples, maybe you're limited to such ideas. Yes?
Are we allowed to put points in the same place?
You are not allowed to put in the same points in the same place. That's a great question, but you're not allowed to put points in the same place. Yes?
Do the prism thing and keep doubling the number of points, the degrees get like
So I didn't quite understand. So you say if you put,
Do the prism thing,
yep.
like keep translating in different directions.
So you want to take this example and keep translating in some direction. I think you will run out of room pretty quickly.
No, I mean like, just copy it
Mm-hmm.
and move it over by one.
I see. You want to take this configuration and translate it in some unit direction. Well, then you double the number of points, but you don't actually increase the number of unit distances that much.
Don't we get each point having like one extra unit distance added?
Okay, so the suggestion is we take some configuration. We take some configuration, let's say this graph G, and I form two copies of G by translating G in some unit direction, some generic unit direction. Okay, great. So what happens to the number of vertices? So n goes to 2m, and the number of edges goes from m to 2m plus n. Is that right? Okay, great. So if you do that, what do you get? N log n. Okay, yeah, that's much better than before. Okay, good. Good, good. Very nice. Yes?
I'm not quite sure what this would get. Let's start with the construction for n over 3.
Uh-huh.
And then replace each point with a triangle.
Right, so the suggestion is to start with some graph G, and then I'm replacing, so let's, as an example, look at that one, and then I'm replacing each vertex here by an equilateral triangle. But I want to maintain the same unit distance, right? So the,
So you just choose an smaller equilateral.
okay.
Or you choose an orientation of this equilateral line triangle so that point's different.
Is this similar to taking this graph G and then translating it in two different directions that form an equilateral triangle? I think it's, yeah, so it's a very similar idea. And maybe you do a little bit better in terms of constants. Okay, yeah, all are great suggestions. And actually, this is really nice. Two times, you want to make a constant correction. Okay, let me just do that. Right. Okay. Any more suggestions? Okay, yeah, all of this is really nice. Okay, so let me tell you what is the best construction that people are aware of. And this is a construction due to Erdős. And the idea is to think big, not build from small examples. So what Erdős did is to consider a square grid of root n by root n. Okay. When I see something that's root n, it's not an integer, just think round down to the nearest integer. I have a square grid. Now, if you take these distances as unit distances, well, okay, you get something which is linear in n, so you don't gain that much. But you can take any specific distance as your unit distance. So what we can do is take a distance that is represented many times in this grid. So let's take the unit distance to be a distance root r, where r is some integer that can be represented as a sum of two squares in many different ways. So for example, if we can take some r so that it has many appearances. And if you know some elementary number theory, then you might know that the best way to do this is to take R to be a product of primes that are 1 mod 4. In any case, you can do this, and you can use some analytic number theory to calculate if you choose the best possible value of R, how many distances do you get? So that calculation was done, and it turns out you get n raised to the power of 1 plus some constant c over log n unit distances. Okay, so this is better than the constructions we've seen before. So what can we say about this problem? So this is a construction. Well, then you want to understand some upper bounds. Right? What can we say about the upper bounds to this problem? And let me show you a fairly easy upper bound, which can be deduced very quickly from the Kővári-Turán theorem. That every set of endpoints in the plane has at most on the order of n to the 3/2 unit distances. So not quite this bound, but it's some bound, right? So the trivial upper bound is n choose 2. So it's much better than the trivial upper bound. Okay, so here's the proof. So let's consider the unit distance graph, which is basically the graphs I've been drawing, where you have the vertices, the points, and I join an edge between two vertices if and only if their distance is exactly 1. I claim this graph is K2, 3, free. Why is that? Because if you have 2 points, what are their common neighbors? Their common neighbors must all be at distance 1 from each of the 2 points. So their common neighbors must lie on the intersections of the unit circles centered at these 2 points, and they meet at most 2 points. Okay, so it's K2, 3, free. Therefore, the Kővári-Turán theorem tells us that the number of edges in this G is upper bounded by n to the 3/2. And that's it. Okay, that gives you some upper bound. Okay, any questions? Okay, so it's an application of Kővári-Turán where we design a graph that has to be K2, 3, free, and the extremal number tells us some information about this graph. What is the best bound that we know? So it turns out we do know how to do a little bit better. But not anywhere close to what we believe to be the truth. Okay, so the current best bound is on the order of n to the 4/3. And we'll actually see a proof of this later in the course once we've developed something called the crossing numbers inequality. Okay, so this is also a very short, very neat proof. I want to tell you about another problem which looks superficially similar and also a really interesting geometric problem. And this is the Erdős distinct distances problem. Which asks for the maximum number of distinct distances among n points in the plane. Sorry, the minimum, thank you. The minimum number of distinct distances. Right, so maximum will be very easy. Okay, again, you have lots of examples. In fact, you can look at basically all the examples that we've given earlier. I mean, these two problems are very much related to each other. Right? You see, if you want lots of repeat distances, or if you want very few distinct distances, right? So they seem like they're very much related. And of course, you can also just write down an inequality that relates the two of them, because the number of distinct distances is at least n choose 2 divided by the maximum number of unit distances. In other words, the number of distances that can be repeated in any single configuration. Okay, right, so each of the examples that I just erased. So for example, if you put points on a line, you have n-1 distinct distances. And we already saw the square grid, so that might be a good candidate to look at as well. And there, it takes some more number theory to figure out how many distinct distances there are. And this roughly corresponds to the number of, so the number of integers that can be written as a sum of two squares. And so this has been calculated, and the result is n divided by square root of log n. So that's the order. Okay. And Erdős conjectured that this example should be more or less the best you can do. Right, so these problems look very similar, but actually this problem here was solved in a spectacular fashion about a decade ago by an important paper of Guth and Katz. So Larry Guth is in our department. And they showed that every set of endpoints in the plane generates at least on the order of n over log n distinct distances. So not quite what Erdős conjectured, but nearly there. And in fact, all the previous results were much worse. Right? So they were off in the exponent. But this one more or less got to the truth. So this is a very sophisticated result that used lots of amazing techniques, ranging from the polynomial method in combinatorics to some algebraic geometry. And that's, I just want to mention it for cultural value. Okay, any questions? Yes?
For the unit distance problem, what is believed to be the bound?
Yeah, so for the unit distance problem, and actually for the distinct distances problem, the question is what is believed to be the bound, and that it's the square grid. Right? So maybe you can do slightly better, but it is conjectured that you cannot do much better, let's say by more than a constant factor compared to the square grid. Yes? Sorry? So this is Nets Katz. He's at Caltech. Okay. I want to take a short break now. And when we come back, I want to show you some ways to generate lower bounds to the extremal number. In the Kővári-Turán theorem, we understood some upper bounds for the extremal number. So I want to turn our attention now to lower bounds, which means constructing, in some sense, graphs that have lots of edges at the same time being KST free. There are many classes of constructions, so there are several techniques for doing this. And I want to introduce you to some of these techniques. And the first one comes from the probabilistic method, where we use a randomized construction. By taking the graph at random, modifying it a little bit in a way that's to our desire. This method is very powerful. It is very general. It is applicable in a lot of situations. But unfortunately for the problem of getting tight bounds, it rarely allows you to get tight bounds. So it is very robust, but somehow it's often not sharp. And another class of constructions that are algebraic all the sharp examples come from algebraic constructions. And there we're able to use some nice ideas from algebra, from algebraic geometry to get tight constructions. And you could wonder, is there some way to combine the best of both worlds? And it turns out this was an important recent development that was found just several years ago, where one can combine ideas from the two and obtain a randomized algebraic construction. And that leads to a new source of constructions for large H-free graphs with many edges. Okay, so the plan is to show you how these constructions work. Okay. First, let's begin with randomized constructions. As I mentioned, this construction is very general, it's very robust, and we can use it to obtain H-free graphs for every graph H. Of course, when H is not bipartite, then we saw from the Turán graph that that's pretty much the right thing to do. So you should think about bipartite graphs H. So fix a graph H with at least 2 edges. Otherwise, the problem is trivial. The claim is that there is some constant C such that for every n, you should think of n as being large, there exists an H-free graph on n vertices and having lots of edges. And we will show that you can obtain the following number of edges. So 2 minus number of vertices of H minus 2 divided by the number of edges of H minus 1. Okay, don't worry about this expression in the exponent. It will come out of the proof. Okay? In other words, the extremal number is at least this quantity here. All right. How good is this bound? So it's some scary-looking expression in the exponent. So let me just give you some special cases for comparison to the Kővári-Turán theorem. For KSTs, the bound, this construction gives you a lower bound, which is of the form n to the 2 minus s plus t minus 2 divided by st minus 1. Okay, so I use this symbol, this bigger twiddle, to denote dropping constant factors. In particular, setting s and t to be the same, we find that the KSS extremal number is lower bounded by this quantity here. Okay, so how does that compare to Kővári-Turán? In Kővári-Turán, we saw that KSS is at most 2 to the n to the 2 minus 1 over s. So there's a bit of a gap. And in particular, even for 2 and 2, these results tell you a lower bound on the order of n to the 4/3 and the upper bound on the order of 3/2. Right? So I'm just doing this explicitly to show you that even in some sense the simplest case, there's a gap between these two bounds. Later on, we'll see a construction that shows that the right-hand side is tight. Right? So this is the truth. The randomized construction gives you something, but it doesn't give you the truth. On the other hand, I want you to notice that if t gets very large as a function of s, this exponent here approaches 1 over s as t goes to infinity. So for very large values of t, at least in the exponent, it's not that far off, although you never get the right exponent for any specific s and t. Okay, so this is some limitation of the randomized method, but it's very robust. And in fact, you can use this result to bootstrap it to a slightly better one for some graphs H. So for example, one might do better by replacing this H by a subgraph, right? Because if you have a subgraph H prime and you construct your G to be H prime free, then it is automatically H free. But maybe this theorem actually gives you a better construction when restricted to H prime. And when can you do better? Well, you can do better if H prime is such that whatever the quantity that comes up in the exponent, so let me write it like this, is superior to the exponent you would obtain by just looking at H. So let me give a name to this notion here. So let me call the 2 density of the graph to be whatever quantity here that would be the maximum if you're allowed to pass down to subgraphs. So the 2 density of a graph H, so denoted in literature often as M sub 2, to be the maximum where you are allowed to look at subgraphs, let's say on at least 3 vertices to avoid degeneracies, of this ratio that comes up in the expressions. So then the theorem, that construction there, implies that the extremal number is at least not just the expression I've written, but maybe sometimes you can do slightly better by passing to a subgraph. So let me give you a concrete example. Suppose my H is this graph here. Okay, so you can run the calculation and find what these numbers are. So the number of vertices, edges, and this ratio here to be 5 vertices, 8 edges, and 7/3. And the idea here is that it's more helpful. Right? So I want to create something which is H-free. But dense things are easier to avoid. Right? So if I have something which is a fairly dense core, that's easier to avoid. So maybe it's better to, instead of looking at the whole H, look at this K4. So if you can avoid K4, of course you avoid H. And maybe it's easier to just avoid K4 and not worry about some of the extra decorations. Right? So if you look at this H prime and go through the parameters, you find that it is like that. And it is somewhat denser in this sense compared to looking at the whole graph H. So you can improve on this theorem for some graphs H where you can pass to a denser core. Okay. Any questions so far? Yes?
Why is this measure called the 2 density?
The question is, why is this measure called a two density? So that's a name given in literature. Partly has to do with these extra ratios. So there are other notions of densities that actually we'll see later on. So this term we'll only see today. So it's more of an ad hoc term for the purpose of this course. Later on, we'll see notions of density that are more relevant for our discussions. Any more questions? OK, so let me show you how to prove this theorem. The proof is very intuitive. The idea is you take something at random, and then you fix it. That's it. Let's consider a random graph. The Adder-Chouinier random graph. So whenever I say random graph, I almost always refer to this one here. And the Adder-Chouinier random graph is obtained by considering n vertices, and each edge, each possible edge appearing independently and uniformly with probability p. And we're going to decide this p later on. Okay, so let me not tell you what p is for now. I'm interested in avoiding h. So this random graph might have some copies of h. Let me count the number of copies of h. We can compute the expected number of copies of h by linearity of expectations. For every possible placement, look at what's the probability that that placement generates an h. Namely, look at all different possibilities for choosing the possible vertices of h. I need to divide it by a factor that accounts for the number of automorphisms of h, but just a constant factor, don't worry about it. And for each of these possible placements, h appears with probability exactly p to the number of edges of h. Okay, just by linearity of expectations. And I can upper bound this quantity very crudely by e to the number of edges of h times n, which is the number of vertices of G, raised to the number of vertices of H. On the other hand, I also want a graph G that has lots of edges, because that's what we're trying to do. We're trying to generate a graph with lots of edges. That's H-free. So the number of edges of G, that's also easy to compute. It's a binomial distribution, and it has expectation P times n choose 2. And basically, I want this quantity to be much larger than that quantity. So I choose an appropriate P. Namely, by comparing these two quantities, I can choose P to be, let's say, 1/2. The half is not important, times n to the v of h minus 2 divided by e of h minus 1. So the exponent comes out of comparing these two expressions. So you see a 1 and a 2. Once you have this P, see that the number, which is the difference, so take the number of edges of G minus the number of copies of H. So I know the expectation of both. I can look at their difference with this value of P. We find that it is at least half of the number of edges. Right? So on expectation, you don't lose too much. Right? So P is chosen so that this inequality is true. Right? So you set what P is. We find that this quantity here is at least some constant times n to the 2 minus v of h minus 2 divided by e of h minus 1. We're still working with a random graph. And we know that this quantity here is on expectation at least that number, so not too small. Therefore, there exists some instance in this randomness, some g, such that the quantity above for the specific random instance is at least its expectation. So this gives us a graph G, which on one hand has lots of edges, but also has very few copies of H relative to the number of edges. So we can now get rid of all the copies of H by removing one edge from each copy of H in G to remove all copies of H, and now we obtain an H-free graph. How many edges are there in this graph? Well, we removed at most one edge for each copy of H. So the number of edges is at least this quantity here, which is what we wrote just now. Okay. And that's it. Right? So now we've obtained our graph on n vertices with lots of edges with the claimed bound that's H-free. So this is the probabilistic method that you start with something random, you try to fix it. And this method sometimes has the name of the alteration method. And it is a very important idea, and one of the key ideas in the probabilistic method, which I encourage you to go and learn more about. We'll also see this method later on when we discuss the randomized algebraic construction.
Just to clarify,
Yeah.
None of the copies of H means not intersecting of copies.
So I mean, so question is, yes, the question is what do I mean by the number of copies of H? I mean every instance of H you see. So they could be intersecting. I'm not asking for disjoint copies. Yeah, so a complete graph on n vertices has n choose 3 triangles. Okay, any more questions? Okay, so now we've seen that the probabilistic method gives you, some bound, and it's not too hard to apply, but it doesn't give you the right bound. Right? It doesn't give you the truth. So now I want to show you a different type of constructions, namely algebraic constructions that do allow you to get the truth, but they work in only a small number of cases. So it's more magical, but they work better when the magic happens. So let's discuss algebraic constructions. In particular, I want to show you how to obtain the tight bound on the extremal number for K22, namely a 4 cycle. So this is a result due to Erdős, Renier, and Schoch. And tells us that the extremal number for K22 is at least 1/2, basically up to asymptotics, times n to the 3/2. Actually, if you look at the constant that came out of the proof of the Kővári-Schoch-Turán theorem, it is also 1/2. So as a corollary, we see that the extremal number is like that. Okay, so this is one of extremely few cases where we know the extremal number so well. Okay, so the constant, if you go back to the proof of Kővári-Schoch-Turán, you see that the constant actually there is 1/2. Okay, so I want to construct for you a graph that has no 4 cycles and has lots of edges. Okay, so that's the name of the game. And I'll describe this graph for you explicitly. So this graph has a name. It's called a polarity graph. Let's suppose that n is a number such that 1 bigger than this number is a square of a prime. So our construction will use some finite fields. I'll explain a bit. If n is not of this form, then you can change n to a number very close to it of this form, and everything will be okay. The graph will be constructed as follows. The vertex set will be the plane over fp. Let's remove the origin. So it has n points exactly. And the edges are such that I put an edge between xy and ab if and only if the equation ax plus by equals to 1 holds. And this equation is meant to be read in fp. Okay, so that's the graph. That's an explicit description of this graph. So I need to show you two things. One, that it has lots of edges, the claimed number of edges. And two, it has no force cycles. Okay, so let's start with not having force cycles. So why is it K223? So what would the K22 be? So let's consider 2 points. So, and I want to understand the number of common neighbors of these 2 points. Well, look at the description for the edges. What are the neighbors? Well, the neighbors correspond to solutions to this system of equations. And the basic claim is that there's at most one solution, xy. Okay, so it's basic fact in linear algebra. You have to be slightly careful in case AB is a multiple of A prime, B prime. But actually, in that case, you have no solutions anyway. Okay. The second claim, then, is that this graph has lots of edges. Well, actually, that's not too hard to show either. So I claim that every vertex has degree. Okay, so how many edges come out of every vertex? I'll give you a comma b. So how many x comma y satisfy that equation up there? Basically for, well, okay, so one of x and a and b is non-zero. So for whatever value of, so let's say a is non-zero, then for whatever value of y you set, I can find a unique x that solves the equation. I have to be slightly careful because I don't allow loops in my graph. So I might lose one edge because of that. In any case, every vertex has degree exactly p or p minus 1. Okay, so just solve that equation in x and y. So the p minus 1 comes from no loops. Therefore, the number of edges is equal to the claimed bound. Okay. So this finishes the proof in case when n has that special number theoretic form. But we can extend to all values of n like this. If n doesn't have that form, then I can take a prime P may not necessarily be exactly satisfying that inequality, but I can always take a prime pretty close to it. So I can always take a prime which is up to a negligible multiplicative error what I want. And then we use, and such that P squared minus 1 is at most n, and use the above construction and add isolated vertices to finish the job to get exactly n vertices. And the reason that I can always take a prime very close to it is because there's a theorem in number theory that tells us that for n large enough, I can always find a prime which is slightly less than n, but no more than a negligible multiplicative factor of. Right? The best result of this form is just, I'm just telling you something in number theory for cultural reasons. So the best result of this form is due to Baker, Harman, Pence. And so this is the question regarding how large can gaps between primes be. So you might know the Dirichlet theorem that tells you there's always a prime between n and 2n. Right? So what about between n and n plus 2n? Actually, we don't know that. Right? So the best result of the form is that there's always a prime. So for n sufficiently large, there exists a prime between n minus n to the exponent 0.525 and n. Okay. In any case, this number here, whatever it is little o n, and that's enough for our purpose. Okay, so it suffices to look at n of a special number theoretic form that where you're allowed to use primes. So that's the construction there. Let me show you an interpretation of that construction, which I think is maybe helpful to think about. And that's that you can view it as the incidence graph between points and lines in projective space, in projective plane. So I start with a projective plane. So I can view a bipartite version of that construction. It can be viewed as the point line incidence graph of a projective plane over a finite field. And by this, I mean put on as one vertex set the points of the projective plane, and on the other side the lines. And I put in an edge between a point and a line if and only if the point lies on the line. So you can do this more explicitly in coordinates if you view them points and lines as coordinates, and so the equation for getting point to be on a line is like that. So now, why is there no 4-cycle? A 4-cycle would correspond to 2 points lying on 2 different lines, which is not possible in this geometry. Right? So that's the reason for that construction up there. Yeah, so no 2 points in 2 lines. Okay, any questions about this polarity constructions? Yeah.
Why is it called a polarity
Right, the question is, why is it called a polarity construction? So it relates points and their polars, which are lines. Yep.
Why does this not have, like, on the order of 2p² vertices if we're looking at one vertex for every point and one vertex for every point?
Okay, the question has to do with a number of vertices here. It's true, here I double the number of vertices, and so I don't get that constant there. But what that graph up there, that's not a bipartite graph. It is identifying the points and the lines and overlaying the two parts into one. But if you don't care about the constants, this graph here may be conceptually easier to think about. Yes?
Are you able to generalize this polarity graph to K?
Great. Question, can you generalize this polarity graph to K33 and higher? So that's what we're about to do next. Okay. So for K33, what can you do? So the main observation here is that two lines intersect in at most one point. Right? But there are other geometric facts of that form. So we're going to use one of them to get K33 free graphs. And this construction is due to Brown. That the extremal number for K33 is also at least factored 1/2 minus total 1 times, okay, so now what's the exponent? What is predicted by Kővári, Turán is 2 minus 1/3, right? And Brown obtains the correct exponent. It turns out this is also the right constant, this 1/2, although it doesn't follow from the Kővári, Turán theorem I stated. One needs to do a little bit extra work, but it turns out it is true that this is also the correct constant. And that's actually pretty much all the cases where we know the correct constant. And there are other cases where we know the correct exponent, but these things tend to be hard to come by. Okay, so let me show you how to construct this graph. So it's based on a similar idea as the polarity graph. It has some more technicalities, so I'm not going to do the full proof and just give you the sketch. As earlier, and using the same trick, we can assume that n has a special form. Here, let me assume that n is a cube of a prime. I'm going to put as edges. So first, the vertices of my graph are going to be points in the affine plane over Fp. Previously, the lines had to do with, previously the edges had to do with lines. And now, let's use spheres. So the edges have the form where I join two vertices like this, if and only if they're, well, it's not really a distance, but it's something that looks like the equation of a sphere. Where U is some fixed non-zero element of Fp. You may have to be somewhat careful in choosing this U, but let me not worry too much about it. So you fix some so-called distance, even though it's not a distance, and I join the vertices whenever they satisfy that equation, having that, not distance. Okay, what's the intuition here? The intuition is that I want to avoid, okay, so how do I know that this graph has no K33? Well, first, let's think about what happens in real space. Right. So intuition in the real space, well, here I have this graph that's, let's say, the unit distance graph in R3. So the neighborhood of each point is a unit sphere. And what I want to know is that if you have 3 spheres, 3 unit spheres, how many common intersection points can they have? 2 spheres intersect in a circle. And that circle cannot lie on the third circle. That you should think about. So that circle intersects the third circle in at most 2 points. So 3 unit spheres have at most 2 common points. And so the unit distance graph in R3 is K333. That entire argument, even though I expressed it geometrically, it's an algebraic argument. You can write down equations on intersections between 2 spheres. It's the intersection of the sphere with its coaxial plane. I have a couple of these coaxial planes. They get me a coaxial line. That line has to intersect the sphere in at most 2 points. You should actually do this algebra if you want to do the proof, because there are funny things that can happen in finite fields. For example, maybe the sphere contains a line. But you choose your parameters correctly, and these things don't happen. And that's the intuition. And if you actually work this out, you find that this graph here is indeed K333. Okay, so I'm skipping the details. But you should do the algebra if you want to have a proof. On the other hand, it also has lots of edges. And that's basically the same reason as before. Right? I can count the number of edges by fixing some x, y, and z, and look at how many ABCs satisfy that equation. Okay? And that's, again, something that needs to be checked. But point is that this graph, so every vertex has either p squared, okay, so it has close to p squared degree. So lots of edges, and combining with basically the same ideas as before, you get the construction. Any questions? Okay, so where can we go from here? To construct the K22, by the way, if you construct K22 free, the same construction works for K23 free. Right? If it's K22 free, then it's also K23 free. K24 free. So here, likewise, this is also K34 free. Okay, so now what about higher KSTs? And you might think, well, let's take these geometric objects and try to extend them further. But that actually seems kind of difficult. We do not really know how to do it. We do not know how to obtain a construction which is of this form that works for K44. In fact, there's even some evidence that that might be impossible. As I mentioned, K44 is a major open problem. Okay. It is an open problem to determine the order of the extremal number of K44. But in any case, this construction, this idea of using algebraic constructions is very enlightening, that we should look at ways to get large KST-free graphs by coming up with clever algebraic constructions. And next time I will show you a couple of very nice ideas where you can come up with a different kind of algebraic construction which has some superficial similarities to what we've seen today, but that's really of a different nature. So next time, we will see the following theorem, which is obtained in a sequence of 2 papers, union of authors, Alon, Kolar, Ronnie, and Zhao, that shows that if T is much larger than S, so S minus 1 factorial plus 1, then the extremal number for KST is on the same order as the upper bound determined in the Kővári-Turán theorem. Just to be more explicit about what these S and T are, if you plug in what's the smallest t that this theorem gives for various values of S, find 2, 2, and 3, 3. And the next one is 4, 7. And then it gets worse from there. So these constructions are based on, they are algebraic constructions. And so we'll see next time what happens.